Alright guys, this problem is a review for two reasons. One, we're going to review no mass problems, or no mass, no problem problems. Why not figure out how to write problem? Okay. Second thing is we're just going to review shifting the axis. So here we have an object that is going to be sliding down the hill. We know its coefficient of friction, we know the angle of the hill, we know the acceleration, we do not know the mass. So we're going to do force diagram first. Force gravity goes straight down, force normal goes up and perpendicular, and force friction goes straight back. So for the shifting of the axis, we talked about the fact that we want to match the direction of acceleration, which is technically down the hill. We can also see that that is parallel. So the easy way to set that up is to draw your axes, which is kind of dotted lines here, one perpendicular or straight through force normal, and the other parallel or straight through force friction in this case. From here we can now sum the forces. Now if we were trying to get friction, we see friction in a problem, we should probably go get force normal first. So we're going to sum the forces perpendicular first, because mass times acceleration perpendicular. This is going to cancel to zero because there is no acceleration perpendicular because of how we shifted the axis. The sum of forces perpendicular should be positive force normal minus the force gravity that's perpendicular, aka this section right over here. Okay? And that's equal to zero. So force normal is equal to force of gravity that is perpendicular. And if I look at my triangle over here, I can see that this was just shifted by the 30 degrees because that came down 30 degrees right there. So my triangle should look like this. The magnitude of the hypotenuse is mg. Here's force gravity perpendicular and force gravity parallel. So that one is adjacent. Since it's adjacent, the force gravity perpendicular is mg times cosine of theta. And this is where we would usually plug in numbers, but since we don't have mass, this is not exactly possible. What would we do with this number, with this force normal? If we had it, we would calculate force friction with mu times force normal. So I'm going to do the same thing, except rather than a number, I'm going to plug this in for force normal. So there comes mg cosine of theta. And again, we would get a number here, but we don't have a number here. So let's do what we would normally do with force friction. We're going to sum the forces parallel. It's mass times acceleration parallel. And if we come back and look at our force diagram, we see that the forces are going to be negative force friction since it is back left. And this force gravity parallel is going to be in the positive direction. So we have positive force gravity parallel minus force friction equals mass times acceleration parallel. And if you plug in this, do this trig, you look over here, like we did a second ago, and we see that this is opposite of the angle here. So that's going to be mg sine of theta minus friction is this mess that we calculated here. And that's equal to mass times acceleration parallel. Or actually, we can get rid of that parallel part because it's all parallel, so that's all the acceleration. Now, if we look at our whole equation, you will notice a mass in every single term. If I divide mass in the first one, I would cancel here. Divide the second, cancel there. Third, cancel there. So acceleration is equal to g sine theta minus mu g cosine theta. And that's why we don't need mass. We just carry it along and move it like normal. So I'm going to go ahead and plug my numbers in. G times the sine of 30 degrees minus 0.4 times g times cosine of 30 degrees. If you plug all that in, you get 1.51 meters per second squared. And that's how you do one of those problems.